Integrals. Now, before we begin with integrals, what do you think integration stands for?
It's the opposite of differential when you're taking the derivative of something.
True. It's the opposite of derivatives. Yeah, definitely. Like we say subtraction and addition are opposite to each other. So similar to that way, or multiplication, division are opposite to each other. Similar to that way, you can call integration is opposite to derivatives, differentiation. But
It's
if I am
also like a
asking,
family or a set of curves.
sorry, can you?
So a family or a set of curves.
Integration is not a set of curve. Okay. So to give you a better perspective, where okay, let's assume that you have a coin. Okay, not
Yeah.
one coin, you have multiple coins.
Yeah.
And if I ask you what is the weight of the coin, okay, what's the
Yeah.
easiest weight of all the coins? What is the easiest way for you to do it?
You add the weight. Sorry, you multiply the weight of one coin by the number of coins.
Correct. That is if each coin is the same weight.
Yeah.
And if each coin is different?
Then you keep adding the different weights till you get the final answer.
Correct. So you add the weight of each coin and you get a total weight. Okay.
Yeah.
This process, what you're thinking of, is called summation.
Yeah.
Okay. You keep on adding is summation. But let's assume I show you the weights. I show you the coins. Okay. But
Yeah.
instead of letting you take the weight of each coin and add it, I melt all the coins, make it a single bar rod. Then what do you do? You don't have.
I didn't understand.
You don't have an option
I have
to weight. Okay, you don't have an option.
Yeah, I can weigh the bar.
Yeah, it's a bar. Yes, not a bar. You can say a cylindrical rod, maybe.
Yeah, so I weigh the rod, and the weight of the rod is the weight of all the coins.
Correct. But let's assume that now after I've made the bar, right, you do not have an option to weigh it, but you have an option to measure the dimensions.
Okay.
Okay, you don't have an option to weigh the bar. You can't get the actual weight directly, but you can measure the dimensions.
Okay, so in that case, you can use the density of the material and then the volume and then find the mass.
That's correct.
The weight.
Correct. So you use the formula for the volume and then you multiply it by density to get the weight. Now, okay, let me modify the question a little bit more. You know the density, okay?
Okay. Yeah.
Your radius and your height, okay, or the length, whatever you call it, is varying.
Sorry, sir. I couldn't hear after you said radius.
Okay. Your radius of the bar and your length of the bar, okay, they are varying.
No, so I couldn't hear anything.
Am I audible?
So your voice is breaking a little.
Oh, just give me a second. Just a second. Yeah, let me know if my is better.
Yes, sir.
Okay. So let's say that the radius and the length of the bar are actually not constant but changing.
Okay.
Okay. You cannot apply the pi r square h formula to find the volume.
Yeah.
Now how do you find the weight?
You can okay, so you take the smallest radius and the largest radius. So that will be like your limits for this thing, and then you can take like a very small portion of the bar, like a small length, a small radius, and you can find the volume for that, and then you can like input the upper limit and the lower limit, basically integration with the limits.
Correct. So you understand that integration is summation.
Yeah.
Okay.
Yeah.
Do you understand this?
Yeah.
Okay. So integration is actually summation, to say in simple terms. The definite integral is where basically you have a limits. As you know, when you do simple integration, that is without the limits, you can have something called as a constant of integration.
Yeah.
Okay. Whereas if you do with the limits,
you get the plus c term.
Yeah, the plus c term. That's called the constant of integration. That plus c will actually get cancelled if you are doing with the limits.
Yes.
Okay. Now within the multiple integrals, to understand, we are going to talk about two separate things. One is the double integral, one is the triple integral. Okay. The double integral is where you are going to find the area under the curve or area within the curve, area enclosed, basically.
Yeah.
Okay. That is double integral. Whereas triple integral would be the volume.
Yeah.
Okay. If you are given the density, then volume can be multiplied by density to get you the mass.
Yeah.
Okay, so that's about multiple integrals. 1 second. Siddharth,
Yes, sir.
give me 5-10 minutes. I'll be back.
Yes,
Okay,
sir.
I'll
Yeah.
mute myself.
No problem, sir.
Okay, so I'll share. Okay, so we were talking about multiple integrals. Okay,
Yeah.
in multiple integrals, as I was saying, when you are doing the double integral, it is the area that you're measuring, area under the curve or area enclosed within the curves. And
Yeah.
wherever it is a triple integral, you will have the volume enclosed
Yes.
in the 3 dimensions. And if you know the density, you can calculate the mass. So let's start how exactly you begin with. So area under the curve when you're doing, just to give you, I'm not sure if I'll be able to draw that over here, but let me try. Let's say you have the xy axis. I'm sorry if it does not look like an axis, and then you have a curve. Are you able to see the screen? Hello, Siddharth, are you there?
That's fine, sir. Yes, sir.
Okay.
Yeah, I can see it, sir.
Okay.
Hello, sir.
Yeah. Hello. There's a bit of lag, I believe.
So I think there's a delay. Yeah.
So this is area under the curve, where you can say that this
Yes.
particular distance is, you can call it as dx. Let's say that this particular height is y, and therefore you can say, and if you want to find the area between a and b, so that will be an integral of y dot dx
A to B.
a to b. Okay, where you expect that y is a function of x.
Yeah.
So you can simply write this as okay, f of x dx, and this will be also be a to b. Is that clear?
Yes, sir.
Now in this particular case, what you're having is one of the uh, axis, okay, or in a double integral you will have two variables, y and x, whereas in a
Yeah.
triple integral you have three integrals, x, y, and z. Now over here what's happening is
Yeah.
your variable in x, okay, or how do you put it, not variable in x, you are actually doing the integration in terms of single variable. So this is not, this is the area
Yeah.
under the curve, but this is a single integral, this is not a multiple integral.
Yeah.
Correct.
We'll need one more curve for a multiple integral.
That's correct. You can do multiple integral over here as well. You can have a dy by dx. You can, instead of doing this, say you are doing only a small one over here,
Yeah.
having a dy dx, dy being the height, dx being this, that becomes your
Yeah.
double integral.
Yes.
And you will need the limits for both dy and dx.
And dx.
Okay. Now the integral for
Yeah.
the limits for x is known, a to b.
Yeah.
Okay. So you can probably, because this is a fixed limit, you can put a to b over here. Whereas the integral for dy will be this particular height, which is varying. So you will write it
Yeah.
as 0 to f of x.
Okay.
Which makes it a double integral. And whenever you're doing a double
Yeah.
integral, you will have something like this, where only the outermost,
One limit isn't expressed.
correct, only the outermost closed integral will be constant, whereas the inner integrals will also have limits, but will be in variable terms.
Yes, sir.
Okay. Let's go back to the PDF. Okay. So the definite integral a to b f of x dx is defined as the limit of the sum. Now what is happening over here? This is your summation.
Yeah.
Okay. Like I said, for each coin you are adding the what do you say, masses or the weights of each coin you are adding. Okay. That is what is happening with this summation over here. Got it? Okay. And n tends to
Yeah.
infinity. Why n tends to infinity? Because in an integral Okay, this is what is happening is, if I just assume like the one as I told you, the bar with radius changing, length changing, etc. What you can do is you can simply cut it into smaller pieces of coins, and then you can weigh each coin.
Yes.
Correct. You can do that, but there will be some kind of an approximation.
Yeah.
Moreover, let's assume if you're doing it that way, there would be some approximation error coming into picture.
Yes.
Which will, the more the number of coins, more the error will keep on accumulating. So your final answer might not be eventually very good if you do it that way.
Yeah.
So basically, you want to avoid the error. So the smaller it is, so not in terms of doing it split thing, but the smaller it is, the error with respect. Okay, why is this? Why do you want it to be smaller? So let's look at the curve again. You see the y, what you see over here in this particular aspect, that is this particular thing.
Yeah.
Whereas you understand for the dx part, I can change the pen. This particular area is not getting, or it is an extra part in your addition.
Yeah.
And
yes.
If you do this error for each of those dx, which means your error will accumulate.
Yeah, and it's going to be huge.
It is going to be huge if the dx is huge.
Yeah.
So you want dx to be as small as possible so that your error reduces.
Yeah.
And that's why your n tends to infinity.
Infinity.
Okay. And the length will be as small as possible, which will give you a better estimate. Okay. Now the multiple integrals are definite integral. If it's a two, as I said, if it's area, it is two variables. If it's a volume, it is a three variable. The integrals of a function of two variables over a region in xy plane are called double integrals. The integrals of a function of three variables over a region in xyz plane 3D are called triple integrals. Applications we have already discussed. Find area, find volume. Did you have mechanics in your first semester?
Yeah.
Yeah. So you can use that to find the moment of inertia, the center of gravity. Moment of inertia comes into the volume integral part, whereas the center of gravity for a plane, for an area, okay, the center of gravity for a plane can be done using the double integral part. Okay, so let's look at the double integral.
We've had all that topics. We haven't used the integration. We use the integration only for the derivation.
Okay, you did not.
We had basic mechanics and mechanics of solids.
Okay, but you did not apply integration for that. Maybe because you
no,
you had standard figures probably.
we used the formulas directly. Yeah, we had the standard figures: triangles, semicircles,
Understood.
rectangles, etc.
So just in case if you do not have standard figures, then you'll have to use integrals.
Integrals. Yeah. Okay. We had to derive the standard thing for everything using integrals, though.
Understood. Yeah, the derivation obviously comes through integration because you have to understand how you get to that particular formula. That's why. Okay. Moving further, double integrals. Consider a function f of xy of the independent variables xy defined at each point in the finite region R of the xy plane. Okay, you divide R into n elementary areas. Elementary area in this case means small areas which you can measure. Okay, and xr, yr be any point within the rth elementary area. So you are doing a double integral, which means you are looking to find the specific area, and so you have a function, you have an area, and the sum of all of that, that is your summation. This summation, the limit of this sum, if it exists as the number of subdivisions increase indefinitely, is defined as the double integral of f of xy over the region R, and is written by this f of xy dA. Now dA, when you're doing, okay, you will, because you have a double integral, you will later split it into dx dy.
Yeah.
Because if it's a double integral, which means you will have the d part should be in two variables. Okay.
Yeah.
The utility of double integrals would be limited if it were required to take limit of sums to evaluate them. However, there is another method of evaluating double integrals by successive single integrations, and that's what you will be using for your multiple integrations part. So let's look at it.
Yeah.
F of xy.
So we separate the x terms and the y terms basically, right?
Correct. Let's look at it. F of xy, yi is the volume of a cylindrical solid region with the base this and height this. Okay. Geometrically, f of xy dA is the volume of the cylindrical region with the base R in the xy plane, and the top surface is cut off by the surface z is equal to f of xy. Okay, so even though this is okay, so understand what they are trying to solve over here. You have a function, okay, and then you have dA. Okay, dA in itself, when you look at the dimensions of area, okay, that would mean it's a, what do you call, dA is two-dimensional area, right? At the end of the day,
yes, area
is two-dimensional, and you are multiplying it by one more dimension. Okay, so in this particular aspect, this is not the area, but this is actually the volume.
Yeah.
Okay, there seems to be some network issue, but I don't have a better network at this point. So we'll continue, but if in case you...
No, so it might be here also. Because
Oh,
of the rain, it's constantly been raining for some time.
okay, fine. But
Pretty
if in
heavily.
case you want me to repeat anything, do let me know. Okay.
Yeah.
Yeah. So in this case, as we discussed, you have this particular entire area over here on the xy plane. As you can see, this is your xy plane. You have the region R,
Yeah.
and you have something cut above, that is your z function, okay, which is f of xy. So what is happening is, it is a cylinder, okay, but that cylinder is not cut in a straight or a parallel plane to xy. If it had been parallel, then it would have just been a simple height. But your height is actually varying, and that variation is given by f of xy. Is that clear?
Yes, sir.
So you use your formula to find the volume over here, and that volume you will find out using the integral part. So as you see over here, geometrically, this is the volume of the cylindrical region with the base R, and the top surface is cut off. If your top surface in this case is equal to 1, then the integral will become simple dA, and in that case, that dA integral will only give you the area. Is this clear?
That's like taking the... Yeah.
But actually it is not the area. Even if xy is equal to 1, it will be the volume.
Because
volume,
the smallest possible volume, right?
I wouldn't call it the smallest possible volume. It would be the unit volume of the bar with unit height.
Yeah, okay.
Okay, so actually speaking, this is not correct, but the way it has been written, the final thing that you get, okay, the final value that you get is equal to the area of the region R. Okay, but if you're doing it with f of xy dA, then actually it is the volume of the cylinder with unit length. Is that clear? The numerical value of both of them is the same. So it is same as, say, if you consider a circle, right? You have pi r square.
Yeah.
Correct?
Yes.
And you have a value. Now imagine a cylinder pi r square h, where h is 1.
But h is 1.
So
Same
you will have
answer.
the same numerical
Different
value.
units. Yeah.
Okay. So that's what is happening over here. The numerical value will be the area of the region R in this case. Okay. Shall we proceed further?
Yes, sir. Yeah.
Now evaluation of double integrals. Area of the rectangle with sides dx and dy, as I mentioned earlier. Then you'll have this dA written as dx dy. Now whenever you are writing your dx and dy, you have to put the integration limits to dx and dy. Okay. A double integral can be considered as an iterated integral. Iterated means an integral after an integral, repeated.
Yeah.
So you will have something called as an inner integral and something called as an outer integral. When you say an inner integral, that means whatever is the integration sign on the inner side, okay, the limits of that will be the limits of the inner, what do you call, inner variable in D, or the dy is the inner variable over here. So the limits of y will come over here, whereas dx is the outer variable. So the limits of the x should be on the outer integral.
But on outside.
Correct? So expressed as the repeated integral, x1 is to x2, y1 is to y2, f of xy, dx, dy. Actually, it should be written as dy dx.
Dy dx, yeah.
Okay. Now, when both the pairs of limits are constants, x1 is 1, x2 is b, y1 is c, y2 is d. In this case, whether we first integrate with respect to x or with respect to y does not matter. Correct?
Yeah.
That is because you have independent limits. The limits are not dependent on each other.
Yes.
Okay. This should have been a. Okay, because you have an a in the figure over here.
A. Yeah.
Okay. This should have been a. So a to b and c to d.
Yes.
That is what is written over here. Is this clear?
Yeah. Yes, sir.
Okay. Let's move on to case 2. y1 is f1x, y2 is f2x, are functions of x, and x1 is a and b. Okay. So over here, what is happening? The constant.
You have to solve y first.
Correct. You have to solve y first because the constants will go out and the variable part will be inside for you to solve. Here f of xy is integrated with respect to y, keeping x fixed between the limits y1 and y2, and the resulting expression is integrated with respect to x within the limits x1 and x2 later on. Okay, AB and CD are two curves whose equations are so and so. This should have been y2 is f2x respectively. PQ is the vertical strip of width dx. Okay, is this clear?
Yeah.
The inner integral means that the integration is along one edge of the strip PQ from P to Q, while the outer integral rectangle corresponds to the sliding of the edge from AC to BD. This is the whole region of integration. This is the area ABCD. Similarly, we have the following. This is just the reverse case of case 2. In this case, the y is a constant, whereas your x is in terms of function of y. So your integral, inner and outer integral, have actually reversed here or changed here.
Yeah.
So y1 is a, y2 is b, x1 is f1y, x2 is f2y. and you do the integral with respect to x first, and then you do the integral with respect to y. Okay, the figure looks like this. If upper limit or lower limit or both are functions of x, then integrate with respect to y first and vice versa. This is clear?
Yes, sir.
Any doubts?
Nope.
Okay, let's proceed further. What are the properties? Now, most of the integration properties that you have studied will be valid over here as well. Okay, if x comma y and g of x comma y are functions of x and y defined over R, C1 and C2 are constants, then this is a simple linearity property that you studied in Laplace. Similar to that, whenever whatever you have done in your single integration as well, you can do this. C1 f of xy ds, C2, C1 and C2 are constants, can be taken out of the integrals, and g of xy ds. Is this clear?
Yeah.
In the second part, if the region R is the union of two non-overlapping regions, R1 and R2, okay, R is R1 union R2, and R1 integration R2 is null. Okay, when you say non-overlapping, R1 and R2, R1, what do you call it? Intersection. R1 intersection R2 is null. Okay, that's written as written like this. I'm pretty sure you have come across this particular symbol in Venn diagrams.
Yes, sir.
Okay, this is null. Null is, I believe, written like this. Is this correct?
Yeah.
So in this particular case, R1 intersection R2 is null, and therefore you can. It's similar to splitting the integral when you have different limits, but in this case, you are splitting the regions. Now, what does splitting the region means? We will discuss this over some of the problems so that you understand.
Yep.
Next, f of xy is gx into hy, where gx is a function of x alone and hy is a function of y alone. If c and d are independent of x and a and b are independent of y, then you can simply separate the integrals, do the derivation, integration of x separate and derivation of integration of y separate, and that becomes your integration, final integration value. Fourth property. This is the volume of the cylindrical region with base R in the xy plane, and top surface is cut off by the surface z f of xy. We have already discussed this, correct? And if you're just doing the integration of ds, that becomes your area of the region R. Okay?
Yeah.
Now let's come to the example. Evaluate. Now this is, you have an xy square over here, dx dy. So understand dx dy is definitely your area.
Yeah.
Whereas this xy square is basically your function where it is getting cut in xy.
Yeah.
Okay, which means this is your basically surface z, and that entire thing is going to give you your volume. Is that clear?
Yeah.
Okay. Now you see over here, your x function is separate, your y function is separate, isn't it?
Yeah.
So we can simply use this particular property.
Yeah, where we separate the x and y.
You can simply separate the x and y. What do you get? But one second. Just look at how this has been written, okay? Because your limits are not written.
So the x first and then dy.
Yeah, you have to first integrate with respect to x, and then you have to integrate with respect to y, which means the inner limits given are x and the outer limits given are for
x.
Y.
Y.
Outer are y. Yes. So you first do the integration for x. It is x dx. So it is x square by 2. Integration with the limits 7 and 5. 7 square 49 minus 20. 5 square it is 25. You get 24. 24 upon 2 is 12. 12 comes outside, and then you do the integration of y square dy, which is y cube by 3.
Y cube by 3.
Correct. And if you substitute 1 and 0, it is 1 cube minus 0 cube, which is 1 by 3. 12 by 3 becomes 4, and that's your answer.
Yeah.
Whenever you are giving a solution, okay, in this case, you know that it is going to be volume, correct? You know this is a volume, right?
Yeah.
So you have to write cubic units as your answer. Don't just leave it in the number.
Yeah.
Am I clear?
Yes, sir.
So you write cubic units.
Yes, sir.
As at the end of your number. Let's move on. Evaluate 0 to 1, 0 to 1, dy by dx upon root of 1 minus x square, root of 1 minus y square. This, again, you can do a simple, this particular aspect. You can change those integrals, which is possible over here. Sin inverse y, sin inverse x. Sin inverse y and sin inverse x is going to be both the integrals. Sin inverse 1 minus sin inverse 0. You have to look at the principal angles in sin inverse x. Okay, and I believe the principal angles are between 0 to pi. No, not 0 to pi. Minus pi by 2 to pi by 2.
Minus pi by 2 to pi by 2.
Correct. And therefore you'll have pi by 2 minus 0. So pi by 2 is the value of sin inverse one integral. Pi by 2 is the value of the other integral, and therefore you multiply both of them and you get pi square by 4.
Okay.
Over here, what they are missing is actually the value of this is pi by 2. The integral which is solved should have been over here outside the integral.
Yeah.
And you will get
and then this becomes pi by 2 again.
Yeah. So it is pi by 2 into pi by 2. So this something is missing in this step. They have missed the pi by 2 which have been there. Okay. let's move on to the next.
No, okay, yeah.
Sorry, what happened?
No, I thought they took it like as two separate things, and then they got pi by 2 on both, and then they just multiplied it at the
That's
end.
not what they've done, because they have kept this over here.
Yeah.
They should have taken it two separately, which would have been very simple, but writing it equal to makes it worse. This is not, like, without the pi by 2, this is not correct. Okay, let's proceed to the next question. 0 to pi by 2, 0 to 1, y sin x dy dx. So again, you have the y first, so you'll integrate y first, which gives you y square by 2. Okay, and you will put, the sin x will remain, but you will first put 0 to 1 on y square by 2, the limits, and therefore you'll have 1 minus 0 by 2. So you'll have the half, that half can come out. Then you have sin x dx, you put in the integral, that is minus cos x pi by 2 to 0. So that minus sign, if I keep it separate, you have cos pi by 2 minus cos 0, that is 0 minus 1. Minus 1 multiplied by minus half will give you half. The other ways, they have just separated, which is possible in most of the questions over here. Correct?
Yeah, the above questions.
Yeah, all the above questions, what you have seen. This is the best way to write it, so that you are clear with what you're solving. Coming from this particular step to this particular step, okay, this doesn't make sense. You should have separated both the integrals, put in the brackets, the square brackets, put in written the limits of both the square brackets, substituted them. Okay, see, you have written half over here, which is wrong, and then you're simplifying y square by 2 over here. You got my point?
Yeah. Yes.
So this is wrong. This particular step is wrong over here. Okay, from this step, moving to this step is correct, and then from this step, you substitute both the values and you get to half. Okay, this step should have been not written. How do I put it? Can't put a square over here. Anyways, you're clear, right?
Yeah.
Okay, let's move on to the next part. Okay, so over here you have you are given, in the first integral, you are given x is equal to 0, which means these are the limits for x. Correct?
Yeah.
And in the second integral, you have the limits in terms of x, that is x and x square, which means you are clear that this is the limits for y. Okay, and then you have y square x dy dx. So what you do over here, you cannot split the integrals. You will first have to do the inner integral, that is dy first. Okay, so you can keep the
y cube by 3.
Yeah, you can do
y cube by 3x.
Correct, that's correct. X can be kept out of the integration for the moment. Okay, you don't have to keep x in the integration part. Okay, you can keep x dx outside and just do y square dy, which is y cube by 3. Apply the limits x and x square. So you will have
x cube minus x to the power 6.
Yeah, x cube minus x to the power 6, and your 3 which you have can be taken outside the integral. Okay,
with x.
Then x, no, not with x. X will be multiplied inside the brackets.
Yeah.
You'll have x raised to 4 minus x raised to 7. You integrate it. You have x raised to 5 by 5, and then you have a 3. They have kept it over here itself, so you'll have 15. X raised to 8 by 8. 15. This becomes 24. Now you substitute the values. 2 raised to 5 is 32. You substituting 0 will make it 0, so you can ignore it. So 2 raised to 5 minus 2 raised to 8 upon 24, and you solve that, and you get minus 128 by 15. I have to check that particular answer. You can divide up and down by 8, which means it makes it 64. Sorry, it's minus 32 by 3. 160 by 15. Yeah, that's correct. Minus 128 by 15 is correct. Are you clear with the solution?
Yes, sir.
Okay, let's move on to the next problem. A is the area of the rectangular region bounded by the lines x equal to 0, x equal to 1, y is equal to 0, y is equal to 2. Evaluate x, y, dA. Okay. This is simple constants given to you. You can simply split them. X square by 2, y square by 2. Correct?
Yeah.
X square by 2 will be half, y square by 2 will be 2. So half into 2, which is 1. Very straightforward.
Yep.
Okay, but they have skipped a lot of steps over here, which I would not recommend you to.
Yeah, they directly wrote.
Yeah, they have written it indirectly, but I would recommend you to write all the steps. Let's move on. Example 6. Evaluate xy into x plus y dA, where A is the region between y is equal to x square and y is equal to x. So in this particular case, you need to first, I'm not sure if the figure will be given to you in the problem. Okay, if it is not given, you will have to draw this particular figure. In this case, y is equal to x is a straight line.
Yeah.
With a 45-degree angle.
Passing through origin.
Yeah, passing through the origin, 45-degree angle. Y is equal to x square will be a upright parabola opening towards the top. Okay.
Yeah.
And it will also pass through the origin. You can substitute y is equal to x over here in the equation, or on the other side the other way. So you'll have x square is equal to x. So x square minus x equal to 0. X into x minus 1, taking x common, will be equal to 0. So x is either 0, which makes it the origin, or x is equal to 1.
Yeah.
These are the 2 points of intersection between the line and the curve.
Yes.
Okay. After you have got the points of intersection, Then you know your x is a constant. You will write in terms of x, the outer limit. The inner limit will be in terms of y. Understand in the curve that you have, y is equal to x square is at the bottom. So that means that will be your lower limit, and y is equal to x will be your upper limit. Whichever curve is above will be the upper limit. Whichever curve is below will be your lower limit. Is that clear?
Lower limit.
Yeah.
Yes, sir.
You open the brackets, x square y plus xy square. Obviously, you have your y limits in terms of x, so you have to integrate with respect to y first. And then you will do keeping x as constant, and then you will integrate with respect to x. Now this particular question, they have completely skipped all the steps and come to the answer. So my suggestion is solve this particular example as a homework.
6, got it.
Example 6. Okay, I'm just writing the page number, or I can write 9-6. That will be easier to remember. Just let me make a note of it.
Yeah.
Okay, let's look at example 7. Evaluation xy minus y cube ds, where the region R is x comma y, where x is less than 0, sorry, x is greater than 0, less than y, but y is less than 1. Okay, now this is something that you have to understand. Okay, so for you to understand this, you will first draw all the lines. What are the lines? You will draw x is equal to 0.
Yes.
Okay, and you will also draw y is equal to 0. So that becomes your x and y axis.
Okay. Yeah.
You will also draw x is equal to 1 and y is equal to 1. Okay, which gives you this particular figure over here.
The square.
Yeah, you'll get this particular square. Then you have y equal to x as well. You will draw that. Okay, just consider y is equal to x. For the moment, replace the less than sign by equal to, and that is all the lines that you are going to draw. So you have y is equal to x.
Yeah.
Now you have to understand what does less than actually or greater than actually mean with respect to the figure. Okay, so when I say x is greater than 0, it simply means
everything above the x-axis.
Yeah, everything above the x-axis, and you have y greater than 0, which means everything in the first quadrant for the moment.
Yeah.
You also have x and y both to be less than 1, which means it is enclosed within the square for the moment.
Yeah.
Then you have an additional condition saying y is greater than x.
Yeah.
Right? Now you have drawn the line y is equal to x. Okay. So
yeah.
this is the line y is equal to x, means basically these are the two regions now which the square has been split into.
Yes.
Okay. Let me ask you. You know this particular point, right? This particular point will be 1, 1.
Yeah.
You can see the mouse, right?
Yes.
Okay. So this particular point is 1, 1. Okay. And this particular point is the origin 0, 0. Now,
yes.
If you just take any particular point within this particular region, okay, let's say you take a point over here on the x-axis. What is the point? It will be x is some value, but y is 0.
Yeah.
Which means x is actually greater than y.
Yes.
Even if I take any point over here, my x value will be 1.
Yeah.
Whereas the y value will be less than 1.
Yes.
Which means again x is not less than y but greater than y.
Yeah.
So if you take any other point even within this region, the white region, if you take any other point, what you will find is the value of x will be greater than y.
Yep.
Which means this region does not satisfy the condition what you want, y greater than x.
Yes.
Now if you look at the other region, okay, if you come on this particular point on the y-axis, x is 0, y has some value greater than 0, y greater than x. Hello?
Yes, sir.
You agree? Y is greater than x over here on this line?
Yeah.
Similarly, if you take this line, y value is 1, x is some value less than 1, which means y is greater than x again.
Yeah.
That means this upper triangle is the region you are looking for in this particular expression. Does that make sense?
Yes, sir.
Okay. Obviously, on the edges, it will be equal. Okay. But when you're looking at it area-wise, okay, that edge is not going to contribute to area as much as the area itself.
Yes, sir.
Okay. So you are going to choose this particular thing. You will have an equal to sign basically. In the limits, you will have an equal to sign. Okay. So don't worry about it. Now, again over here, you will have the limits. You can have the limits for x as well as for y. You can keep the x constant from 0 to 1, which is given over here. And you will have the limits of y. Lower curve is y is equal to x. So y is equal to x. And the upper curve is y is equal to 1. So you have 1 over here. You will integrate with respect to y first. okay, because your limit of y is in terms of x. While integrating with respect to y, x will be a constant. So x into integral y dy is y square by 2. Integral of y cube is y raised to 4 by 4. You will substitute the limits from x to 1. Okay, you'll put 1 first. So x by 2 into y square 1 and x, you'll substitute 1 minus x square, minus 1 by 4, you'll substitute 1 and x, 1 minus x raised to 4. You can open the brackets, x by 2 minus x cube by 2 minus 1 by 4 plus x raised to 4 by 4, and you integrate again. Now over here the integration is missed. It is x square by 2 into half. So x square by 4 is the first integral. So x square by 4, which means you are putting 1 and 0. So it will be 1 by 4 as your first particular number. X cube by 2 becomes x raised to 4 by 8. There's a minus sign, so that minus remains as it is, 1 by 8. 1 by 4, it is x. Like integral 1 by 4 is dx. So 1 by 4 x. X is 1 minus 0. So minus 1 by 4 as it is. X raised to 4 becomes x raised to 5 by 5. So this entire thing is x raised to 5 by 20. And therefore you will have x raised to 5 becomes 1 raised to 5 minus 0 raised to 5. So which is 1 upon 20. And now you have to simplify this. The overall denominator LCM is 40 multiplied by 10 multiplied by 5 multiplied by 10 multiplied by 2. So 10 minus 5, which is 5. 5 minus 10, which is minus 5. And this is 2. So 2 minus 5 minus 3 by 40. Is that clear?
Yep.
Now, I'm just asking you a question. And let me see if you understand this.
Yes,
you've got an integral value. And
Yeah.
the integral value is negative. What does it indicate?
The sum of everything is negative.
How can the sum of everything be negative?
Yeah.
Sum, right?
Yeah.
How can sum be negative?
And we're finding an area. Area can't be negative.
Yeah. So why do you think it is negative? What does it imply?
Maybe because we're going against some optimal condition.
Meaning?
I'm not exactly sure how to explain it, but maybe like this method was not to find the area of that particular side and maybe the lower side.
Okay, fine. Just give me a second. Let me put my laptop on charge.
Yeah.
And I will explain you what the negative sign implies. Now, it is something, I'm not sure if we noticed the negative sign before this particular problem. But I thought I'll just ask you, what do you understand by the negative sign? Because that is,
We're supposed to ignore it, right? Like
the answer will remain negative. Okay, the answer is not going to change positive, but there is a reason behind the negative. You know the number line, right?
Yes.
On the number line, on the right side of 0, you have positive numbers.
Yes.
On the left side of 0, you have negative numbers.
Yeah.
So you understand negative does have some implication.
Yeah.
Now, let's get back to the first thing we understood in the double integration. What does this mean? What does the double integration over here give you? What does it represent?
The volume where that plane cuts off our shape.
That's correct. You understand that this is a volume of some rod, okay, with this being your region and this being your height.
Yes.
Okay. Now,
is it negative height?
That's correct. In this particular case, your bar or your surface is not cutting in the positive z-axis, but it is cutting the bar on the negative z-axis. And that's why the negative sign implies that your cutoff is happening below the z is equal to 0 plane.
Yeah.
Does that make sense?
Yeah.
Okay. So whenever you are having a negative sign or a negative answer, do not think that you have done some mistake. It's not necessary. The negative has a meaning. Have you understood?
Yeah.
So most of the integration, if you see, you have got positive because it is in the positive xy thing. Okay. Whatever integrals we have done so far, it is in the xy positive plane, but the negative has a meaning, and I wanted you to understand that. Is it clear?
Yep.
Okay, let's proceed further. Evaluate xy ds where r is bounded by y is equal to minus x is equal to root y, and y is equal to 1. So very first thing is you draw all these lines. You have y is equal to minus x. So the equation is y is equal to minus x, but they have written y is equal to x, which is not correct. Okay, the line is drawn correctly, but it has been written wrong. Then you have then you have x is equal to root y, or you can simplify this as y is equal to x square.
Yeah.
Okay. 1 second. Okay, y is equal to x square, which gives you this particular equation. Curve, the parabola, upright parabola opening towards the top. Then you have y is equal to 1, which will be your this particular line parallel to the x-axis. So you have got all the curves, and now you have to solve this. Now over here, it is very clear. You have this particular line. So your value of x is changing. over here. Similarly, your value of x is changing in this side of the curve. What is not changing is basically, or what are constants is basically your limits of y. Okay, your y starts at 0 and goes up to 1. So your limit of y is a constant, whereas your limit
So,
of,
but we have to take the base as the y is equal to minus x line, right? Hello?
yeah, I'm listening. 1 second. Y is equal to minus x, y is equal to 1. Oh, okay. This is the region where they have split the region set completely.
Yeah, two regions.
Yeah, they've made it 2 regions. But you could have done it a single region as well, if you look at it. Okay, yeah, so this
Yeah.
the single region is
Y
done over
goes
here.
from 0 to 1.
The single region is done over here,
Yeah.
where you put the limits for x in terms of y. Okay,
Root y and x.
yeah,
Minus 1.
this is a very straightforward thing where your lower integral, okay, when you're doing in terms the limits in terms of y, your lower limit is the one on the left and the upper limit is on the one on the right. Okay, and therefore you have x is equal to minus y, this
Yeah.
particular line which is coming, that is on the lower limit, and x is equal to root y, that is your upper limit. Okay, and then you can
Yeah.
simply do the integration with respect to x first. You have xy dx, so it is x square by 2. X square by 2 half goes out, x square, so it is y and minus 1 second, x dx is x square by 2, so it is going to be y minus y square. Oh, it is going to be y minus y square. Okay, this is wrong. This is the
Yeah, okay.
integration, this is the integral value with dy.
Yeah.
So this is wrong. So it is going to be y minus y square. Okay, and that you will integrate, which will be y square by 2 minus y cube by 3, which will be half minus 1 by 3. Half minus 1 by 3 is, half minus 1 by 3 is 1 by 6. What's wrong? One second, did I do something wrong?
So it'll be y square by 2. That will be the integral inside. And then when you're substituting y square values, we'll get root y the whole square, which will become y. And then we'll get the,
yeah, so
oh no, that's x.
yeah,
Sorry.
x dx is x square by 2.
Yeah.
Sorry.
So we'll get y and y minus y square we should get.
Correct. That's what I was thinking.
Yeah.
Y minus
And
y
that
square.
becomes,
That will be y square by 2 minus y cube by 3.
2 minus y cube. Yeah.
And then you're substituting 1 and 0, which will be half minus 1 by 3. Half minus
Yeah,
1
half
by 3
minus
is
1 by 3, 1 by 6.
1 by 6.
That gives
Half
us 1
into
by
1 by
12.
6 is 1 by 12. Okay, let's look at the first solution. Let's see if there is any mistake over here. In that case, the value 1 by 12 is correct. Let's see. So they have split the regions, and you have a triangular region over here and a parabolic region over here. So minus 1 to 0 and minus x, minus 1 to 0, where the value of y is minus x to 1, and 0 to 1, where the value is from x square to 1. So let's see. You're doing y dy first, so it is y square by 2. Y square by 2, half goes out, y square 1 minus x square. 1 minus x square, you integrate, it becomes x minus x cube. Now this should be x cube by 3 after the integration. Do one thing, do this problem.
Yeah.
Okay,
Exactly.
evaluate page 10, 8th question, and you have, okay, that's the end of it. So we are going to do till 11, so you have this problem as well. So let me write it down. Page 10, 8th question.